So before I talk about the spooky and the weird parts, let's talk about why you would even care about Quantum 2.0 or quantum in general. And I brought a game to talk about this. So you see these 9 tiles right here, right, with all these different cats. So the goal of this game is to arrange these tiles so that every cat has the right head and bottom in the right color. So you have 9 tiles. I did this for the first 3 where you have the blue cat and the yellow cat. And the other ones are missing still. So you have 9 tiles and you have these 9 spots for these tiles. So you might think about, well, how many different possibilities could there be? I only have 9 tiles. But since every tile can go in each of these spots and every tile can be turned, there are actually quite a lot of possibilities. In fact, there are 95,126,814,720 possibilities for these 9 tiles. We have found one solution so far. There might be more. But if you're going through all of these 95 billion possibilities, that's probably going to take a while. So we want to use a computer to do this. Well, a computer would take 24 hours to go through. Sounds pretty good, 24 hours with 95 billion possibilities. What if we could do this faster? What if we could do this, let's say, in a second? 95 billion possibilities in 1 second. That sounds like science fiction, right? It sounds like such an incredible speed up. Well, that's where quantum computing comes into play. So this is a quantum computer, and it doesn't look like the computers we know. A quantum computer is a machine that uses quantum physics, phenomena from quantum physics, to do calculations, to do computations. And it looks very different than the computers we know. But what is quantum physics? So when we say physics, we usually think about classical physics. So things like, why is the sky so blue? Or what happened to his hair over there with this balloon? Those are things we learn in school, and that's classical physics. Quantum physics is something different. That's the physics of the subatomic world. So we're talking really, really tiny things, atoms and smaller. And it's actually really hard to picture how small an atom really is. Picture I'm holding a little tennis ball, like in this picture here. And on this tennis ball, I put 1 atom, 1 single tiny atom. So you wouldn't be able to see this because it's so tiny, right? And now I take this tennis ball and I grow it. I keep growing and growing and growing until the tennis ball has the size of our Earth. So now it's huge. This atom that was growing with the tennis ball, that would now be the size of a tennis ball. So if you imagine looking down from space onto Earth, and somewhere on Earth is a tennis ball, that's how small this atom was on the original tennis ball. So we're really talking incredibly tiny, tiny things. And when we're talking about things of these scales, these tiny, tiny things, that's when quantum physics comes to play. And really since the beginning of the 20th century, that's when we have started to discover how these things work. And this picture here, that's from 1927, and in the middle there is Einstein with a lot of other people. And those were all the people who found a lot of these quantum rules and figured out how things worked at these tiny scales. And fun fact, there are 29 people in this picture, 17 of these got a Nobel Prize at some point. So says a lot, right? And the discoveries that they made, we actually feel those because that's where we have computers. That's where we have lasers. That's where we have the internet and many other things. And so this was what we call the first quantum revolution. And these technologies, these are what we call quantum 1.0. But what about quantum 2.0? So I said earlier, spooky and weird. I'll talk about spooky and weird and how spooky and weird are driving this next technological revolution. So when you hear spooky, you might be thinking something like this, especially right now with Halloween coming, right? So quantum, that's not about ghost. So spooky and quantum means something different. This is a picture of 2 dice. There seems nothing spooky or weird about this. We're going to talk about weird first now. So why do I show you 2 dice? We all use dice, right? We've probably played with dice in some games. Maybe like me, you've tried desperately to get out of jail by rolling the right 6s. Maybe it worked. In my case, it didn't. But there's still nothing weird about this. But now imagine living in a world where your life is dictated by rolling dice, where if somebody asks you a question, you can't answer unless you roll dice. So let's say I'm asking you, how are you feeling right now? Well, you would pay attention, maybe go, I'm sleepy, or I'm excited. But what if I tell you that's not allowed? This is not how the world works right now. You have 6 possible ways how you could be feeling. Maybe you're feeling cool, or silly, or sleepy, or excited, or angry, or scared. But you can't answer my question until you've rolled the dice. Not this kind of dice, not the Monopoly dice. But a dice like this that has these emotions, these feelings on there. So you would have to roll this dice to answer my question. So let's do this. And my dice says cool. So now that I rolled my dice, I can say, well, you're asking me, I feel cool. But honestly, I could have gotten a different outcome because I had these 6 different possible outcomes. And that's a really strange way to think about a life where maybe you can't really say how something is until you measured, until you looked. Because all you can say is that at this moment, you could get any of these outcomes. And this is what we call a superposition. That's a really big thing in quantum. And all it really tells us is that if somebody asks us, if we're measuring, if we're trying to find out, any of these 6 possibilities could happen. I could say I'm scared. I could say I'm excited. So thinking about a world where you're living like this, that seems weird, right? And you might ask, when does this even happen? And this is exactly the quantum world, the subatomic world. When things are really, really tiny, this is how this all works. And quantum physics, that's probabilistic, which means you're only living in probabilities and odds. So you can only say something like, I have a 30% chance that I'm angry and a 70% chance that I'm happy. And if I want to know which one it is, I have to measure, and then I'll be either angry or whatever the other option was I said. And so that's something that is strange and weird. And when they first discovered that this is how this works at these scales, not everybody was very happy. For example, Einstein, he really wasn't a fan. So he said, it's one of his famous quotes, I, at any rate, am convinced that he, God, does not throw dice. Because it just feels so unbelievable that there would be all these probabilities instead of really knowing what is going on. But honestly, it doesn't really matter if we are comfortable or not comfortable with this, because we actually figured out a way to use this, to do something with that. And that's where quantum computing comes into place. So how is a quantum computer different from a classical computer? I mean, it looks very strange. And this is only one of the possible ones that we have. They all look different, they're all huge, they're all weird. So let's look at a classical computer first. The computers we all work with, they store information in bits. So 1 bit is 1 piece of information. And this bit can either be a 0 or a 1. So if you put your name into a computer, the computer translates everything into zeros and ones. And a good way to think about it is this little switch here. If the switch is in the on position, that would mean the value is a 1. And if it's in the 0 position, in the off position, that is a 0. And if I check, it's a 1. There's no uncertainty right there, or it could have been a 0, but it's set. A quantum computer uses a quantum bit. We call this a qubit, and that's different. It can still be a 0 and off, or a 1 and on, but it could also be like in this little dimmer here, it could be somewhere in between. So in this case, when it's right in the middle, that would be a superposition state, like earlier when I talked about these feelings. This little cloud would tell me, I actually can't say anything more than if I measure, if I ask, what value are you? I have a 50% chance of getting a 0 and a 50% chance of getting a 1. And the crazy thing is, because I can store more information in a qubit, 1 qubit can take 2 pieces of information. If I just have 100 of them, 100 qubits, I can store more information than all the hard drives of the whole world. And I'm sure there are more than the ones I did, but at some point I was like, this is enough. I'm making more computers. And if I take 300 of them, then I actually can store more information than I have atoms in the universe. And that's an insane number. I think it's 10 to the 84. Don't ask me how they know this, but it's a lot. So 300 qubits. And all of this because I can make this qubit be in the superposition state, where I just can only say, I might get a 0 or I might get a 1. So keep in mind, this probability or this capability of having these two pieces of information, that's only until I look. Because if I look, I'm going to get either a 0 or a 1, and then I lose my special feature, my special quantum feature. It's like flipping a coin. And what can we do with this? We can use this for quantum computing. And I said earlier, as my intro, quantum computing might help us solve the cat puzzle, right? That's something we could do. We could go through these 95 billion possibilities in 1 second. But we can do more. We could, for example, figure out what's the fastest way from Flagstaff to Disneyland. And differently to a classical computer, we could look at all of these different routes at the same time and just get instantaneously the correct one, the fastest one. Or I could use it for drug discovery, and I could look at all these different combinations at the same time. So basically anything that is very complex, like climate change, that's really good for a quantum computer. I could also use it to factorize number. For example, 546, that's 3 times 7 times 2 times 13. That's something I can do with a quantum computer. So this sounds good, and it is. Factorizing is good, but there's a downside. A lot of our encryption relies on factorizing. And so if we can use a quantum computer to factorize things, that means we can decrypt and we can hack and we can steal secrets. So that's not so good. So there's a downside, right? There's some risk we are getting with quantum computers. But luckily, we can use quantum physics also to protect our information. It turns out we can use light, using quantum physics, to send very secret messages. And understanding how this works is actually something we can do by looking at things in our environment. So you've probably been at a lake at some point, right? And you've looked down and then the light shines onto the water. Even if the water is very shallow, maybe you just see the reflection of the trees, or you see your own reflection. You don't see what's in the water. And if you're lucky, you have something like this. You have polarizing sunglasses. People who go fishing love them, because what they do is they filter out certain light, and by doing this, you can suddenly see what's actually in the water, because you can remove these reflections, you can remove the glare. And we can actually, with quantum physics, use these polarizing sunglasses to send secret messages. So I have to be fair. You can't just do it with a flashlight and sunglasses. You need to find a way to have your light so reduced that it's only one photon, the smallest amount of light that you can have at a time. So you're sending one photon at a time using these polarizers, and you can send these secret messages. And there's something else that's cool. If somebody was trying to spy on you, if somebody was trying to look at these messages, your message would change. And so you could actually tell that there was a spy, and you just stop using this. So this is something you can then use to encrypt your data, and nobody can hack it because only the sender and the receiver had this secret message. So this was the weird. Really quickly, I want to talk about the spooky. The reason that we call this phenomenon spooky is also because of Albert Einstein. He, again, wasn't really a fan. This is called quantum entanglement. And a good way to understand what it does, the outcome is if we go back into our pretend world where we are the ones living with these quantum rules. So here are two people, and like before, these people would have to roll a dice to answer how are they feeling right now. And their answers would not be related, right? Maybe I'm asking the first one and he's sleepy, and maybe I'm asking the second one and this one is excited. And the next time I'm asking, the first one is still sleepy, but this time the second one is sleepy too. There is no correlation between the outcomes of when I ask them how they're feeling. But using quantum physics, if those are really, really tiny particles, I can bring them together and I can do something that's called entanglement. I can entangle them together, and by doing this, I can link them in a really, really strange way that correlates the outcomes. So if I now ask my first one, and he says he's sleepy, I will find that every time I ask the first one he's sleepy, the second one was excited. So suddenly the outcomes are correlated in a way. It's as if they were holding hands or talking, but they're not. And the craziest part is, if I take one of them and I put it on a spaceship or something and send it to Mars, this would still work. I would have the same outcome. And it's instantaneous, so it's not like somebody sends a message and says, hey, I'm sleepy, you have to be excited, because remember, we're supposed to be in this together. The interesting part is, though, they're very, very fragile, these things. So I would actually have to put both of them in really, really cold fridges. And this quantum entanglement, that's not something that we experience, but these quantum particles experience. That is something that will be the main resource for us when we want to build a very new internet, a quantum internet. That's actually something I am working on, making this new internet. And there will be many things we can do with it. Most of them we have no idea yet. Another thing we could do is teleportation. So you might have watched Star Wars, Star Trek is the right one. Star Trek at some point was like, beam me up, Scotty. So I'm not saying we can beam anyone. We won't beam people because that's way too much information. But we can actually transport information from one point to another. So instead of putting my information in a fridge and sending it somewhere, I can teleport the information from one location to the next. And those are just two examples of all the things that we can do with just the spooky part. And with this, I'm just going to stop. And I don't know if we're ready, but it's coming. Thank you.
Thank you. That was terrific. I don't know how many talks you guys have seen about quantum mechanics and physics, and I'm assuming a few or maybe none, but I'm guessing a lot of them were not necessarily accessible where you could actually follow what the science is. So this is terrific because for people who are not in the field, once we start hearing about entanglement, that's an easy place to get lost. So I appreciate these really interesting pictures. So unfortunately, this Festival of Science, I feel like we've had a couple negative bits of information. So I don't know who saw the keynote, which was a lot of fun, but the speaker came out and said, we're trying to clone things, but then said, we're not cloning dinosaurs, so we can't. So there's a lot of sad faces, but still can do some amazing things with cloning. And now you just told us that we can't teleport.
Well, we can teleport, just not you.
Okay.
Right? So when I have my students calculate teleportation when they learn it, I always start with the teleport, and then later on when they realize we're just teleporting qubits, it's like, man, but they did teleport. I mean, they learned how to do it, just not people.
Okay.
Yeah.
So what I got out of this is maybe.
No people.
Well, Ines, that was terrific. I really appreciate you spending so much time talking with us, talking about quantum. It seems like the world's going to change, and just you said yourself, in a way that maybe we don't necessarily know, and we'll find out. But thank you for giving us that introduction. So a big hand for Ines.
Thank you so much for having me.